Well, I mean, the last topic we are going to cover today is collision actions. In fact, this is a topic which is not covered by any, we have a wind code, earthquake code, life load, dead load code, but we don't really have a collision actions code. But then I realized that in the highway design code, we do have some sections on collision load, but we actually have a look at it because there is a really a scope for really a lot of R&D in this space. So some 12 years ago, I was really motivated to really get into this area because there are, relatively speaking, there have been a sort of a relatively lack of interest working in this, and our colleagues work on ballistic impact and on blast explosions. So I thought that maybe I can actually make a contribution into this space, looking at sort of more civil engineering applications of collision action. So in the short course, you will also have lectures on collision actions forming part of the short courses. So this 15 minutes presentation by myself is just focused on this particular topic. So collision actions, you do actually have a lot of reports from journal articles in Australia itself and internationally. And normally you will actually be in the journal articles is about presenting a lot of tests, impact tests, and also simulations, dynamic simulations. But I was really reading a lot of these articles. I said, look, perhaps the practicing engineers are looking at something else. They like to really look at some concepts rather than saying, these are all the test results and data and charts. And we want to really understand how should we actually visualize impact actions, collision actions. Can we actually summarize it in a few algebraic expressions? And it's like what we do with statistics. Can we do it? So we are aiming at trying to really develop concept which is transformative and irreversible. So that means that when you actually understand those concepts, you actually change the way you think. And it's not something that you can easily forget. And it's irreversible is that once you accept and understand this is how you approach a collision actions problems, that you would not actually look at another way. Probably that is too rigid. I'm saying that when you really encounter another method, you will try to reconcile anything which is new to you and absorb it in and really further mature the methodology. So let's really look at something very, very simple. And you would say, well, we have collision actions is hypothetical, a boulder hitting on a baffle on the pole. And what we normally do in engineering, at least in the highway code of practice, is we apply equivalent static force. Now that's, I feel that most engineers look at it, that's reasonable enough. This is how we have been operating all the time. This is really how the code stipulate collision actions. So try to make things simple. There's nothing wrong with it. Replace it by a static force. But let me just really look at a scenario where initially you have got a pole, a shorter one, and you have a taller pole. And we find that with a taller pole, it actually resists the impact better than a shorter pole. We find that with a taller pole, the bending moment at base is smaller. The diffractions, according to statistics, the diffractions is really proportional to the height of the pole raised to a power of 3. But in fact, it is not quite that rate with impact action. So with bending moment, definitely you are getting less and less bending moment as the pole becomes taller. They'll say, why is it? Because energy is a product of displacement and force. And this is why when you actually allow more energy being absorbed with a taller pole and you displace more, then the strength demand accordingly get less. And another thing is if you put a dummy mass on the pole, and what happened is that the impactor hit that dummy mass, then a lot of the energy actually pushed back to the impactor. We're getting it to rebound. So the energy doesn't get that much of energy get down the pole. It's been repelled. So we also learned that in reality, you know, you put more and more dummy mass at the top, you actually reduce the bending moment at the base of the pole too. And the last one, you put a cushion, a rubber cushion or anything, or recycled materials as a cushion. And what happened is the cushion actually delay the transfer of momentum. Because it's all about momentum transfer. It delayed the transfer of momentum. What is the consequence of that delay? Is that you actually get time for the support from the ground to get sucked up to the dummy mass, and the dummy mass actually get larger as far as the impactor sees it. So the cushion would further reduce bending moment at the base of the pole. But however, if you go by statics, you don't get any of that. So static doesn't actually reflect any of those phenomenon, which has been well proven by experiments. And you can actually see that in reality, the bending moment get less and less and less, but static force doesn't. So in the way that we just simply say, although that the Australian highway code doesn't get into that, it's sort of being stipulated an equivalent static load, but for argument's sake, this is really the well-known eco-energy method stipulated by Eurocode 1. So you say, well, that force is actually the velocity of impact multiplied by the mass of the truck multiplied by the stiffness of the parapet. And that's really what actually determines these equivalent, so-called equivalent static force. But now, can we actually assume this to be the fixed end of the parapet? And you see that by the principle of statics, what happens there shouldn't really affect the bending moment there. We learned it from day one in our first year engineering statics. So, but in fact, we learned that if we instead put the fixity here, then the fractions of the cantilever slab actually contribute to more deflections, and hence the rate of K decrease and the force decrease. So if you go one step further, I mean, this is really an analogy to what I actually showed there. You actually increase the flexibility, you reduce the strength demand. But however, there's a lot of catch up to do with the British code, with the British code, that it hasn't quite really gone along this pathway of reasoning. So when the bridge is founded on deep sediments, so tall piers, deep foundations, there's significant rotations of the power caps. And that would actually contribute to more deflections. And as a result, there is a huge reduction in bending moment down, not only on the parapet itself, but down the bridge pier. So you can actually see that deflections, getting the bridge deflected more would actually help a lot, because we learned from our undergraduate degree that deflection is normally checked last, because you say, oh, you check for safety, stability. In the end, you check for serviceability. This is why you calculate deflections. But with dynamics and impact actions, deflections is really central to the whole safety and stability of the structures. The deflection behavior is not about serviceability only. So you really have a somehow paradigm shift in the way we look at impact actions. Now, and also we get back to the dummy mass argument, and we have actually derived this expression which actually incorporates dummy mass, because at the moment, if you want to, you say, I appreciate that, but then the challenge nowadays is you can't really find much reference from quotes and from books or from any articles about how you actually get it quantified by just an algebraic expression without going the trouble into getting a lot of simulation, take hours and days, and you're not sure whether you got it right. But a simple expression is what engineers like. According to what my experience with interacting with practicing engineers. is that you increase the dummy mass, the bending moment get less and less and less. And that's not factored into any codes of practice which deals with collision actions. And last, cushioning. Well, you say if a vehicle rams onto a barrier, it's not a hard object because it has the front of the vehicle crumbles. And that crumbling is really an analogy to cushioning because it delays, there is a delay in the transfer of momentum. Now, when we've learned about equal momentum principle when we are at school, but in that case, our physics teacher also looked at that dummy mass there, but without a stick, because it was a physics class, not structure class. So there is no issue of any energy being sucked up from the ground and causing cushioning. So our physics teacher didn't teach us that. But in fact, that is what the school physics teacher taught us is really part of a bigger picture. That you have dummy mass mitigating structural actions, and with cushioning, it is even to a bigger extent. So that's why we have also done, our knowledge of Dr. Scott Menegon here and my former student Arnold Yong derived the cushioning factors for different types of trucks. Really going through some months of work in simulations to get the cushioning factors here. So summary of key points. So yes, we like to really make design simple. Yes, we like to really retain the static method of analysis, fine, but make sure that you observe some fundamental principles. Energy, the trading off of force with space. So if you violate that principles, then yes, it's no surprise that what you actually get down on the calculation pad doesn't reflect real behavior. And also take into account of Newtonian mechanics, inertia generated by target mass. So there's nothing new, but what is new is that we have yet to incorporate into design. And cushioning. So it's also dynamics. And I think that we also need to revisit the way we educate our students is that statics is absolutely fundamental. But we should also introduce timing as the dimension early on in engineering education. So we haven't actually quite done enough to introduce the time dimensions when we're dealing with structural analysis. So we have actually not only say, oh, we just come up with this expression, we have actually done lots of tests. And also acknowledge so Dr. Scott Menegon really helped supervising students back in 2018 and 19, doing lots of tests to really educate us. And now we also have got a method of working out how much impact would actually produce permanent indentations on the wall and how much would cause spalling of the wall and how much would cause punching of a wall in a collision scenario. And we also put sort of, this is in the rockfall barrier design, we put gabions filled with pebbles acting as cushioning. So that cushioning is not necessarily really pillows, cushions, rubbers. It can be in any forms which delay the transfer of momentum. So including the crumbling of vehicle or even gabions, they are cushions. They are very effective cushions. So we are about to really roll out a textbook, which is about 400 pages in length, and we actually make good use of 2010 to 2000, starting in early 2020, we have been offered a book writing contract by Tay and Francis. So we get together a team of Dr. Arnold Yong, myself, and Dr. Scott Menegon, spending the last sort of 20, almost 30 months writing up this book, which is going to be published in September this year. It really goes, the first two chapters look after all, readers who have low prior knowledge on dynamics, but you have some knowledge on dynamics, you may skip the chapter 2 and get straight on the chapter 3. Then after chapter 3, you may pick the topic of your choice. So we have actually spent a lot of time writing up 2 chapters on bridge stack collisions, and also a collision on concrete. And Dr. Scott Menegon in particular put a lot of contributions into this area. And you also have collision on the pole found in soils. That is also put a special allotment from Jude Saliva Pereira, Dr. Jude Pereira, who actually maybe he's still here or he has gone. Really, his research have actually been put into the book. So we have also got a chapter which is about 100 pages long, really guiding readers on how to set up your own Excel spreadsheets to simulate that in your own hand, in your own self-prepared tools, how to really undertake impact dynamic simulations using your own program. You write your own program on Excel spreadsheet and do it. And finally, we have a chapter showing how much all the experiments we have done to validate all the theories we present in this book. So it's not just about theory derived. We present the derivation of theories. Importantly, we have also all these theories published, accompanied by physical experimentations in a large scale in the laboratory to provide support. So this is going to be rolled out in about 3 months' time. And this is it, and very happy to spend time having a chat with you.